Good morning. Welcome to episode number 33 of the Zoomtown experiment. This episode is all about garbage. Yep, all about garbage and how Micropython deals with garbage, or I should say Python in general. This whole episode here is a result of some problems I've been experiencing developing the code up to almost this point. Weird little problems that would come up here and there that made no sense at all. And frankly, I had to dig into it, and it was quite a journey, so I wanted to share it with everybody. What we're talking about is a function of Micropython or Python called the garbage collector. The purpose of this function, which runs automatically in the background when there's too much garbage, so you can't really predict it. But what it does, as you can imagine, your program, you use local variables within a function, then you exit the function, and then you go about doing some other stuff, and you come back into that function and use another local variable, etc. Well, all those variables that you create and abandon, well, they're still occupied memory spaces. So the garbage collector's function is to go around and clean up after our mess, essentially. In other languages, a little lower level languages, often the programmer is required to perform that task. But in Python, Micropython, etc., it's doing that work for us. Otherwise, we'd simply, as the program ran for a little while, run out of memory, and things would even be much worse. Well, as you can imagine, that garbage collector, when it does run, it's got to go through and do a substantial amount of work through the entire program and memory system of the computer, etc. So it takes time. As you know, I've been very focused on my deterministic loop for this program from beginning to end, or to present for that matter. And that's where I discovered what was happening. As you know, we're focusing on keeping it at 5 milliseconds, and a lot of what we're doing, if you haven't noticed, really depends on things to happen every 5 milliseconds. If they happen infrequently or in variable periods of time, the estimation of acceleration distance, the catching when our rotary encoders roll over from 0 to 360 degrees. If we don't catch that action within a reasonable period of time, the data that's being presented to us from the encoder can be misinterpreted, thus causing what appears to be math problems, which was really at the core of a lot of this discovery process. So let's start first by just looking over what's going on right now at this date on Zoomy 11, which is our incremental programs that I've been putting out with each episode, and for episode 33. Now, as you know, I've been monitoring memory usage, cycle time usage, etc. since the beginning of this project. And I verified it again yesterday, and our memory, our stack, number of blocks, all this data is looking really, really good. I don't see any trouble here with where we're at with the program. Here are all the different function times. This is during an actual processing of MQTT communications. That doesn't happen on every loop cycle. It happens on every 6th loop cycle. And that isn't necessarily, I'm trying to minimize the load here on the PICO. It's more to reduce network traffic, because every time through that loop cycle, I'm sending out all the telemetry data over to the scheduler. With just one Zoomy, that ain't a big deal. When you got 16 of them, it starts getting to be a lot of data that you're looking at. But our current loop time is 4.57 milliseconds, getting very close to my 5 millisecond target. So in essence, looking at this, we're in good shape, right? I shouldn't see any delays in my loop. Now the way I measure that, and we've been through this before, here down at the bottom of our main loop, I print out the difference in time between a CP0 and a CP7 timestamp. And that is, yes, I know the main loop's really muckety right now, but I got to have other data in there. Here is when I record the start time for the main loop, going all the way through down to here is I mark the end time for the main loop. I am currently not counting the time it takes to execute this, or obviously the print statement, or all the way back up here, this particular statement, this counter incrementer. So there's a little bit of additional time that is being spent in this whole process. But this is what I'm printing out. Now I'm going to run the program. We'll take a look at that data just real briefly. Before I do that, I want you to look at this statement right here. This is what happens, or this pops up on your screen in Thani when you click your stop button and it reboots the PICO-W. See this version 1.22.2? That's a really important thing to keep an eye on. And I'll explain why here in a little bit, but pay attention to that number. Let's go ahead, run this program. What we're seeing here is a column of two sets of numbers. The set on the right is the actual time right here. That's our run time of the loop. The time over here on the left is the time that up to this point here, the actual work I'm performing. Remember, these few lines of code here delay the loop. Literally, it just sits here doing nothing in this time until we reach 5 milliseconds. So this is showing the work being done. Now what I'll do, I'm going to expand this a little bit so you understand it a little better. Right here, we've got a big number, 4.298. Let's ignore that one. We'll start here, 2.689, 2.578, 2.7, 2.6, 2.5, and then another big one. Well, that is our every sixth cycle where we then perform MQTT communications. So 1, 2, 3, 4, 5, 6. And that, at that time, is executing all of this information here. So nothing mysterious here. Everything is as expected. Let's go ahead and plot that data. And I'm going to do that. As you know by now, one of my favorite tools is a spreadsheet. And the reason why I like spreadsheets is that I can plot out data to tell me something very quickly without having to dig for that data and refine it further. Here is our two columns, A and B, where that data came from. The A column being the actual amount of time that was used up, and then B showing me how precisely or consistently our 5 millisecond time is running. Over here on the graph, you're going to see that column A is this blue line, column B is the red line. Now right here, you see that this is right between 4,000 and 6,000 microseconds, so that's 5 milliseconds. That is what we would expect to see, a perfectly flat line, except we've got these massive spikes of time here. This was where the devil was hiding for me. Let's just zoom in and look at a range from about here to about here. I believe that's this one. Now we can see a little more detail of what's going on. Over here, most of these are about a 2.5, and that would be this line right here at the base of all these spikes. That is our normal running cycle time. The point of these blue spikes is our MQTT communications. Boy, that just makes it very visible, very obvious what we're looking at data-wise, right? Then the red line here is this column here, and I've put it right in a spot where we can see what's going on. We're at essentially 5 milliseconds all the way through, with the exception of these cute little bumps here. But then here we spike up to just under 14 milliseconds. That's a lot. That's a heck of a lot of time being wasted on something, and I couldn't figure out what. So again, using spreadsheets to see data is a very powerful tool in our world. Now I'm going to go back to this one, and we see it happens pretty regular, right? It's happening at a given frequency. And every time it runs the garbage collector, magically it takes time. And that's what we're seeing up here. Now I'm going to go down or go to another spreadsheet, this one, and this one. Okay, now what was happening through this whole discovery process to understand this problem? I had been talking online in a couple of different forums and reaching out to a few of you viewers. Tomek, for one. Thank you very much, Tomek. I appreciate all your help and assistance. We were really narrowing down, this has got to be garbage collector, but why so long, etc., etc., etc. And early on in this process, when I was running an older version of the software, the numbers were much worse, like 3, 4, 5 times worse than what we're seeing in the data that I'm presenting to you, because I didn't understand it yet. But here you'll see that we're just under 16 milliseconds, and we see that frequency. Now, the whole purpose of the garbage collector, to our understanding, was that it's cleaning up local variables that are no longer in use. So Tomek and I and a couple other people, we've all kind of thought about it and thought, get rid of the local variables. We'll run everything global. So I went through, spent a little bit of time, a lot of time doing that, and you'll notice that it really had no effect. This is running a program version that had no local variables. So we thought about it some more and thought, well, another way you can get a program to run much faster, more efficiently, get rid of all the function calls. Maybe it's because I'm calling these functions, going in and out of them so much, the garbage collector's having a lot of work to do. So I literally built the whole program to run inline. I think I only had one function that I was calling outside of that. And you'll notice that it's exactly the same. But maybe a teeny bit worse, up to, that's the funny part. Here we're peaking under 1.6. With everything in the main loop, we're peaking at 18 milliseconds. So it actually got worse. It didn't solve the problem of the garbage collector. Time went on, still poking around, and then I thought, you know, I haven't updated my UF2 file in a while, so I looked at what one I had, and I did have one in my local storage area that was a newer version, so I threw that in there. Lo and behold, I got a whole different set of data. It was very different. Still wasn't good, but I got different data. And I thought, whoa, somebody's working on this. They're seeing it, whoever's creating the UF2 files, the people at Micropython, and they're doing something about the garbage collection. So I thought, okay, I better get the most recent version, which at the filming of all this was 1.22.2, and it got even better yet, a lot better. So whatever somebody was doing there greatly improved what was happening with the garbage collection time. So now let's go to today, back to my graphs over here. And so the first thing I'm thinking of, I got to make the program run more efficiently and try to get these peaks out of the picture here. And one of the ways I thought about is obviously local variables, getting rid of functions. None of that had any positive effects. So I'm thinking, what if I ran another thread and put some of this in another thread, and that way I can have stuff running over in that thread, stuff running in this thread, and balance it out. And the more I thought about that, that got really tricky, because there's a lot of things happening, like motion over time, where if I do something at this point in time and I'm calculating on it at a further back or a point of time, I'm going to get even more messed up data. And so I thought, let's hold off on threading. It's probably not a good solution, but there is the big power play I could pull out of my magic trick. Change the clock speed of the PICO W. It runs beautifully fine at 240 megahertz. So if I run it twice as fast, essentially, will it perform better and more efficiently? Well, this is what happened when I did that. Of course, 5 milliseconds is still 5 milliseconds, but all my garbage collection is now happening at a peak of 8 milliseconds. Much better, right? Twice as fast. Makes sense. But there's still bad stuff here. I don't like it. Now, if you're not familiar with overclocking, I will show you that code. And by the way, this code will be available to you. It'll be in our download packet. To add in overclocking, we add this frequency command to our frequency to our machine import. Right next to, I did it right next to the Watchdog timer class. Here I print out the frequency that it was, which once you change it, literally the PICO W stays at the new frequency. So printing it before and after now will show no change because I'm currently running at the 240 megahertz. But this is the command that will set the PICO W to run at 240 megahertz. That's all I had to do to get this data. Huge improvement, right? But it's still not making me happy. So I'm discussing again with Tomic and a few other viewers and people on the forums, and somebody says, run the garbage collector under your control when you want it to run. Beat it to the point where it gets to, maybe it's so overwhelmed that it takes a long time to clean up the garbage. If you run it more frequently, maybe it won't take so much time. Ooh, great idea. Okay, so we will look at the next version of the program. And all the details of that, everything else is the same, but I want to get to the top of the loop. There's a function called GC collect that we can run if you import GC. So I'll go all the way to the top, show you that I imported that. Right here, import GC, garbage collector. Get all the way back down to here. Now before I even enter the loop, I run a garbage collection, just to get rid of everything that may have been created during the boot up process. I'm going to use this counter here to count up to 100. Once I get to 100, so 100 iterations of my 5 millisecond deterministic loop, I will collect the garbage. And then I'll reset the counter, wait another 100 cycles, and collect the garbage. So then I plotted this all out, and wrong one again, bear with me folks. This is what I ended up with. Now, I haven't really fully fine-tuned this yet, and I probably will wait until I've got all the code developed, because there's going to be other influences in here. But right now, everything is under 6 milliseconds. So I'm 1 millisecond away from my target. Now, I could easily just accept the 6 milliseconds and make the cycle continuously run at 6 milliseconds, and I don't believe there would be any ill effect into the performance of the Zoomy software. But as I said, I've got more work to do, and that will have an effect on a lot of this. So at this point, I am going to accept that additional 1 millisecond spike every essentially 100 times through our loop, until a such time where I get everything stabilized, and then I'm going to tweak out my overall machine cycle time, my deterministic loop time. What a crazy journey that was. But the really cool part is during that, I'm thinking back, when I first got into programming during the late 70s, early 80s, there were forums, but you had a 300 baud dial-up modem, and it was not what it is today. So you really didn't have a whole collection of people to just ask for help. Today we've got massive forums very specific to products or things that we're inquiring about. We've got YouTube where we all share information. There's just a lot of resources of information and people willing to help. And so as I'm reflecting back on how I would have dealt with this 40 some years ago, it was fun to go through it today, this crazy problem, and be able to understand it and all that. And then, of course, again, keep using spreadsheets as a diagnostics tool. They tell you a lot of information really fast. Well, that's going to wrap up this episode all about garbage, and I look forward to seeing you next week.